And welcome back to the Neuro Symbolic Channel. I'm Paulo Shakarian, and I am recording this here at Syracuse University. It's a nice summer day, and really pleased to talk about some new research papers using PyReason. So for those of you not familiar, PyReason is a logic programming framework, a similar idea to, say, Prolog. Except unlike something like Prolog, it allows for temporal reasoning. It allows for lattice values to be assigned to be used as truth values, which gives you things like open world reasoning, so direct representation of uncertainty, as well as compatibility with fuzzy logic. And so what's interesting about what we created is that because of this lattice-based truth values, it gives you some more flexibility in interfacing with external external optimization routines. So I would say, namely, machine learning models using PyTorch, and on the other hand, you setting up the optimization problems for a solver, like an integer program. And why would you want to do this? Well, for one, integrating with machine learning model allows you to take in this perceptual information from the machine learning model and then reason about it using logical rules. So let's say we're on a factory floor and we have some best practices that we've maybe developed over a long period of time, and we can change out a human who's looking at an item on an assembly line with, say, a vision transformer model, and that model can give us really good results. Well, then the downstream decisions that maybe normally would have been done by a human can now be automated. And so, but making that link between the ML model and the logic is key. And unlike some of the other ideas that we talk about in this channel that deal more with, say, end-to-end training considering logic, this is more of a practical approach where nuts and bolts, how do you actually code this up in Python in a seamless way where maybe the model is pre-trained, and so we want to do some reasoning about those results in kind of a practical way. The second piece of work is also really interesting. So, PyReason is essentially still a monotonic logic, even though it has a lot of power, and we've talked about this in other videos. But as such, it's not capable of doing certain things like solving a combinatorial problem. But of course, the good news is there's well-established methods for solving combinatorial problems, say an integer programming solver or a SAT solver, and so on. But one thing that comes up with solving a combinatorial problem is usually you're optimizing something, usually kind of a scheduling problem, where you want to optimize one function and use other items as a constraint. And the difficulty becomes there in how do you frame it? So for example, if you just, what if you can eke out a lot more in your objective function and you just slightly violate your constraints? And same with vice versa. So how do you make these decisions? Now, of course, there's, some work on relaxations and stuff like that. But our approach deals with framing alternative versions of the optimization problem based on the user input, kicking them out to solvers, and then taking those solutions from the solvers back in, and then reasoning about those solutions again using logic. So sort of like with the ML model, you're integrating PyReason directly with an external process, letting that process run, and then sucking that information back in to do more reasoning. So both of these papers have been accepted to the International Conference on Logic Programming. And so let's kind of pull that up. I think some of the European listeners, especially those engaged in areas of computational logic, would probably find this conference interesting if you don't already know. I know many do. This has been around for a while. This is the 41st ICLP. And so it's going to be held in Renda, Italy, in September, and they just announced papers that have been accepted. So scroll down, we see that these were accepted as technical proceedings. So here we have machine learning model integration with open world temporal logic for process automation. And then the other paper is, oh, here it is. Reasoning about medical triage optimization with logic programming. So our target application in that use case was looking at medical triage. So I want to show you these papers, but also give you a quick tour of our new PyReason website. This is a staging version, but by the time this video is released, you'll have the actual version of the website will be out there, and we'll put the link in the description. But you have everything you need about PyReason here. We will post updates, and here I have linked those two papers, and I'll go over those in a moment. Instructions how to get PyReason, all of our PyReason tutorials. So those of you remember the pet store tutorial, as well as the tutorials on PyReason machine learning integration and links to the docs. And then we have a whole page on all the different applications, a list of all the papers that are using PyReason. And if you have recently published a paper using PyReason, feel free to let me know and I'll just add it to the list. This is not meant to be exclusive to just the research happening here at Syracuse. And so let's go back to the updates page and let's pull up these papers. Let's start with machine learning integration with temporal logic for process automation. So the preprints available on arXiv. So I'll click view PDF. All right, so let's zoom in here a bit. So kind of the main idea is you have some kind of inputs, and we have two examples, one of blackjack and one of a welding robot. And the output of those are viewed with some kind of perceptual machine learning model. I think in here we use either CNNs or vision transformers, which of course gives you output, which comes in the form of a vector, which can give us essentially a confidence level. Now, in turning that into annotated logic, we can turn that confidence level based on implementation decisions into an annotation. And I'll zoom this in a little more so you can see. And so, for example, we might want to have something be annotated with total certainty, or we could have it annotated automatically with total uncertainty. And if this was 0, 0, it would be falsehood. But you can also do things where you could have, say, keep the upper bound as 1 and make the lower bound be whatever the confidence is by the model. Or you could make the lower bound 0 and have the upper bound be the confidence. Or you could have both be the same thing. Or you can add in a tolerance that can just subtract that confidence by a certain number. So the API gives you a lot of options. So what happens now is we have this machine learning input, and it produces new atoms based on the API that can be thrown into the logic program. Now, there's existing rules in the logic program. So if it's detecting a gap in the weld, for example, then in the next time step, it would want to try to repair that. And so once these rules get thrown in, we've updated new things at a certain time interval. So time is very important because we're envisioning that this goes on over time. And then the PyReason inference engine draws new conclusions. And so if it's repairing, then that would be an example of an atom that could lead to an action. So if that's concluded by the inference, now we have something that goes back to to your agent and gives new instructions to repair the defect. Likewise, to keep on checking it as time progresses, there is a level of pulling. So you have the logic program that resides in memory, and over time, it's pulling the machine learning model to get new updates to atoms that look like this, if there's a gap or not in the well. And so as it's doing that, you get the logic program gets the constant feedback, and we design the API in a way that when it pulls, it imports these new atoms, it reruns inference to draw new conclusions, and then it goes and interfaces with the rest of the code. So if there's like, hey, it's time to repair, then that goes back to the agent. So this is very nice because you have now a good API written in Python, and this is available in our latest version of PyReason. The next thing described is turning the predictions into facts. So let's see if we have, so yeah, this describes how the API works. So based on what the user sets is the probability or confidence returned by the model greater than some threshold. And then we can decide if we're going to make it just be uncertain. So we can say, hey, if the confidence is not at least so much, we just say we don't know what's going on. Or we could proceed with bound decisions, and based on how the user is set up to set the upper and lower bound. And we also have different ways of pulling, and I'll kind of stop right there for now because I want to cover the other paper. But really nice work led by my main PyReason engineer, Duman Aditya, with help from my postdoc, Mario Leyva, as well as our latest addition to the PyReason team, engineer Colton Payne. So let's talk about the second paper, reason about medical triage with logic programming. So this was funded and also done collaboratively with a really great startup called Zimworks out of Colorado. And so the whole idea is that for the target application, you have, say, a bunch of people that need to be rescued due to medical reasons, and you have a limited number of assets. So you see these are medevac assets, so helicopters basically. And you need to make decisions as to which people should be rescued based on their medical condition, subject to constraints such as how many helicopters you have, how long can they be in the air, and so on. And so this is a really important application because it could lead to lives being saved. So it turns out that within the area of medical triage, there's a lot of discussion on the best way to go about optimizing this, so setting up the optimization problem. So the idea we came up with is you have the information from the ground, you have a logic program to frame the optimization problem. So notice this plural. So once the logic program takes the input, it frames them, it creates multiple instances, and now it kicks them off externally to a solver. So just like with the way we interface with the machine learning model that's pulled every so often, here we're kicking off logic program created problem instances to an integer program solver. And then we collect up the results from the solver and we put them back into the logic program, and it can further reason about it based on how that inference progresses, or it can kick out results to a user. So the rules in the logic program are all in the same place. So for example, in setting up the optimization problems, there's considerations as to how to score casualties, because the idea of assessing a casualty, it can be based on different factors, but you might not always have all that information available. So again, we need logic to sort through these different methods and based on the circumstances, assign the right kind of initial triage score to the casualty. And then, of course, how that's done influences what your objective function is, as well as how to set up the constraints, and if we could have different sets of constraints and so on. So in looking through this, we also can provide the different types of optimization results directly to the user in the user interface. So even though it reasons through it, it can still present, hey, this is everything I found out from the different optimization problems. And then based on what you said in the logic, here's what I recommend we do. And so the user interface kind of would allow you to adjust, the weighting of different priorities that the user may have. And so this table here shows logical rules that can be used to score a casualty. So based on if there is certain insults available, so insults meaning like information about the casualty and their condition, as well as, if the vitals are available, how it scores that patient. And then the ultimate scores resulting of the logical reasoning. And then we have a lot of there's a lot of special variables that result from the deduction process, dealing with constraints and dealing with optimization criteria. And so those are set based on the result of the logic. And so what you have here is, after running inference, you create these problem instances of combinatorial problems, and then they're kicked off to an external solver. And we did a series of experiments with simulated data because it's, there's not a lot of real world data on medical triage that's publicly available. But one thing SimWorks does is they specialize in creating simulated data for customers like the military. And we compared it with some standard types of optimization. And basically what you get is you can look at kind of the mix of things and how the results of optimization using our framework compare to the typical baselines, and they significantly outperform. So we had a few different settings here where we had urgency-based, reverse optimization, and situational optimization. And you see, as the number of assets increase, the total number of casualties and the aggregate of the triage score also increases in significantly more than the baselines. And we did further experiments to kind of look into different aspects of this, such as, if you're optimizing for one criteria, but then you use the logic to kind of reason about it and have an acceptable threshold, what happens to these other indicators as you take up the number of assets. So anyway, we'll stop there. For both of these papers, we'll likely be releasing longer videos where we'll go into more complete technical details. The point of today was just to give you a taste. So I hope you find that interesting. And again, please check out the new PyReason website. And don't forget to like and subscribe. Thank you so much.